Welcome. Hi everyone. I am D. Vidya, Assistant Professor of Mathematics, Bharadiyar Arts and Science College for Women, Deviyakuruchi, Attur, Salem. Topology. In this video, we discuss about introduction to topology and some examples. Now we discuss the general information about topology. The term topology was introduced by Zegan Benedict in 19th century, but it was developed in 20th century. The father of set theory is another mathematician to credit for topology. Mathematics have two types of papers. The one is pure mathematics papers, second one applied mathematics paper. It have more branches. Topology is a branch of pure mathematics that deals with the abstract relationships found in geometry and analysis. The word topology is combined two words. The first one topos, it means surfaces. The second one logy, it means study. Therefore, the word topology means the study of surfaces. About topology. Topology have four characterization. The first one is shapes, second arrangements of shapes, third functions between shapes, fourth deformations of shapes. General definition of topology. Topology is the mathematical study of the properties that are preserved through deformation, stitchings, and twisting of objects. Deering, however, is not allowed. Otherwise, measures such as distance and angle are not important, but shapes, relative positions, and arrangements are important. Note, it's sometimes called rubber sheet geometry because the object can be stitched and contracted like rubber but cannot be broken. Example, a circle is topologically equivalent to an ellipse and sphere is topologically equivalent to an ellipsoid. Uses of topology. Topology is used in many branches of mathematics such as differentiable equations, dynamical system, Canard theory, Riemann surfaces in complex analysis, and it is also used in string theory in physics. Definition of topology in mathematics. A topology on a set capital X is a collection tau of subsets of capital X having the following properties. First one, the empty set pi and the whole set capital X are in tau. Second one, the arbitrary union of the elements of any subcollection of tau is in tau. The third one, the finite intersection of the elements of any subcollection of tau is in tau. Examples. Let capital X be a set. It means a collection of well-defined objects. The set contains no elements, one elements, two elements, three elements, etc. for finite case. Here the first example is let capital X equal to the empty set. There is no element. The topology on the empty set is always the empty set. It is trivially a topology. Second one, let capital X equal to set of all A comma B. Capital X contains the two elements. One is the comma A and the second one is the B. The topology on capital X. There are four topologies in capital X contains the two elements. The first one tau 1 equal to its obvious result for topology, it's a power set of the capital X. Therefore, power set of capital X is a tau 1. The second one is contains a topology empty and the whole set capital X. Therefore, tau 2 equal to set of all empty set pi comma capital X. The third one tau 3 equal to it's a collection of subsets. The first one is pi empty set, comma, second one the whole set capital X, the third one is singleton set A. Here the collection tau 3, the condition of the topology first one is satisfied. Empty and whole set is always in the collection tau 3. The second condition is the finite intersection and arbitrary union. A finite intersection, any two elements in the tau 3 or any three elements in the tau 3 intersect of 2 or intersect of the 3 is in the tau 3. The 4 intersection property also hold. The next property is arbitrary union. Arbitrary union, any two or any three elements in the tau 3, it's again is elements in the tau 3. Therefore, tau 3 is also satisfies the union property. Therefore, tau 3 is a topology on capital X. A similar way for the tau 4. Tau 4 equal to set of empty, comma, capital X, comma, singleton set B is also topology on capital X. Next example, let capital X equal to set of all A, comma, B, comma, C. Topology on capital X. The first one is power set of capital X is obviously topology, and second topology is empty and the whole set capital X only contains the tau 2 equal, therefore tau 2 equal to set of all empty, comma, capital X. The tau 3 equal to set of all empty, comma, capital X, comma, singleton set A. These collection contains three elements. The one is the empty, the second one is the capital X, the third one is the singleton set A. These three elements satisfies the topology conditions for 3. Therefore, tau 3 is also a topology. Similar way for the tau 4, tau 5, tau 6, tau 7 and tau 8, etc. Next, some notes in topology. A subset capital U of capital X is an open set of capital X if U belongs to the collection tau. Second, the complement of each element of any topology is again a topology. Third one, the elements of tau is open as well as closed. The fourth one, arbitrary union and finite intersection of open and closed sets is again open and closed set respectively. Next one, the types of topology. There are several types of topologies, here noted for only 4. The first one is discrete topology, second indiscrete topology, third trivial topology, fourth non-trivial topology. The first discrete topology. If capital X is any set, the collection of all subsets of capital X is a topology on capital X. It is called the discrete topology. Example, let capital X equal to set of all A, B, C, D. Here capital X is set. The collection of all subsets of the capital X is a discrete now. Therefore, tau equal to collection of all the subsets of the capital X is denoted by the power set on the capital X. Therefore, tau equal to power set on capital X. That is tau equal to rho of X. Next, indiscrete topology. If capital X is any set, the collection consisting of capital X and empty set pi only is called indiscrete topology. Example, let capital X equal to set of all A, B, C, D. Here indiscrete topology is only the collection consists of empty set pi and the whole set capital X. Therefore, tau equal to set of all empty set pi, whole set capital X. It is a topology for capital X is called the indiscrete topology. Trivial topology. Discrete topology and indiscrete topology are called trivial topology. Non-trivial topology. All other topologies are termed as non-trivial topologies except discrete and indiscrete topology. Next, relationship between topology. First one, finer topology, second kosher topology, third comparable. The first one, finer topology or larger topology. Compared to different types of the topology, it's neither the one is tau and another one is the tau dash. For the same set capital X, therefore let capital X be a set and tau dash are two topologies on a set capital X. If tau dash contains tau, then tau dash is finer than tau, and if tau dash properly contains tau, then tau dash is strictly finer than tau. Example, let capital X equal to set of all a comma b comma c. Here tau 1 equal to set of all empty set by comma capital X comma singleton set a comma singleton set b comma set of all a comma b. Here tau 1 is contains empty and whole, satisfies the first condition for the topology. The second condition, it's arbitrary union. Its arbitrary union, tau 1 contains 5 elements. It's any arbitrary union of the elements is in the tau 1. And the third condition of the topology, arbitrary union also satisfied, the finite intersection also satisfied. Therefore, tau 1 is a topology. Next, tau 2 equal to set of all empty comma capital X comma singleton set A. Here 3 elements contains, tau 1 contains 5 elements. Therefore, tau 1 is finer than tau 2. Next, Cauchy topology or smaller topology. Here also taken two topology on a same set. Let capital X be a set and let tau and tau dash are two topologies on a set capital X. If tau dash contains tau, then tau is Cauchy than tau dash. And if tau dash is properly contains tau, then tau is strictly Cauchy than tau dash. Example, let capital X equal to set of all a comma b comma c. Tau 1 equal to set of all empty comma whole set capital X comma singleton set A. These collections contains 3 elements and 3 elements satisfies the topology condition. Therefore, tau 1 is a topology on capital X. Next, tau 2 equal to set of all empty comma whole set capital X comma singleton set A singleton set B comma set of all A comma B. These collections contains 5 elements. These 5 elements satisfies the topology 3 conditions. Therefore, tau 2 is a topology. Therefore, tau 1 is contains 3 elements. Tau 2 is contains the 5 elements. Therefore, tau 1 is Cauchy than tau 2. Next definition, finite complement topology. Let capital X be a set. Let tau f be the collection of all subsets capital U of capital X such that capital X minus capital U either is finite or is all of capital X. The corresponding tau f is a topology on capital X called the finite complement topology. Thank you.